Number theory is a part of mathematics where you study the integers and their properties. So, for example, let's introduce some concepts like factorize a number. So if I have a number, for example, 24, I can factorize it, meaning that I can write it as a product of two numbers. And there are several ways in this case. So I can write it. I can also factorize it into more numbers than 2. For example, I can write it as 3 times 4 times 2. So factorize a number means write it as a product of numbers. In this case, we're talking about integers since we are considering number theory. So it goes without saying when you're doing number theory, you should work with integers. Some numbers, for example 7, they only have trivial factorizations. You can, for example, write it as 1 times 7 or 7 times 1. But these are the only ways to factorize 7, trivially into 1 and the number itself. Numbers having this property that can only be factorized into trivial, like themselves, of 1, they're called prime numbers. Numbers that are not of prime numbers are called composite numbers. So, for example, 6, that's a composite number because you can write it as 2 times 3. So it has some other factorization than trivial 1 and the number itself. Of course, you could write it as 1 times 6, but it's not the only factorization. So it's a composite number. All numbers, all integers are either prime numbers or composite numbers. 1, you don't consider that to be, you consider that to be neither prime or composite, but it's a trivial example. So, for example, 2, that's also that's a prime number. That's the smallest prime number. And it's also the only prime number that's an even number. All other prime numbers are odd numbers. So the prime numbers are 2, 3, 5, 7, 11, and further on. There are infinitely many prime numbers. This can be proven. An interesting fact, an important fact in number theory is that any number can be written as a unique factorization of prime numbers. And by unique we mean if we don't care about the order of the numbers. For example, 6 we can write as a product of prime numbers 2 and 3. Of course, we can also write as 3 and 2. But disregarding order of the numbers here, there's a unique prime factorization. So every number has a unique prime factorization. And for example, 7, we consider that to be its own prime factorization. That is something you can prove is a very important result in number theory. Another important concept is divisibility. So you say that a number a divides, and that you write mathematically as a vertical line. So a divides another number b. What does it mean? It means per definition that b can be written as an integer, let's call it k, multiplied by a. So b is divisible by a if we can find an integer k, so this holds. For example, 2 divides 6, since we can find a number that we can put here that will make this true, and that is of course 3. Or for example, 4 divides 24, since we can find a number to put here, and that number is 6. And if we cannot do this, then we say it's not divisible. That, for example, 4 does not, and then we write like this. I should write it in a vertical line here. We cross over it. We said 4 does not divide 25, for example, because there are no integers that we can put here that will make this true. There are of course fractions, but we are talking about integers. So 4 does not divide 25. We can also say that 2 is a factor of 6, since 2 divides 6, and 4 is not a factor of 25, since it does not divide 25. For example, here we see that 2 is a factor of 6, since we can write it as a product of two factors, 3 and 2, making 6. So divisibility and factorization are very close to the concept. We can also talk about even and odd numbers. The even numbers are 0, 2, 4, 6, 8, and so on. And the odd numbers are 1, 3, 5, 7, 9, and so on. We could of course also include minus here, but we will see that we will not talk so much about negative numbers, since most of the characteristics we are interested in will be found among the positives. So if I know, for example, that 3 is an odd number, it's very trivial just to say, okay, minus 3 is also an odd number. Okay, another way of saying this, an even number, let's call it m, is even if we can write it as 2 times another integer. So if I can find an integer and write it as 2 times that, then it's called even. This is the definition of even. So for example, 6 is even, since I can write 6 as 2 times 3. And 8 is even, since I can write it as 2 times 4. And the number is odd if I can't do this. If I instead can write it as, you can find a number, k, not necessarily the same as that one, so it should perhaps call it something else, L. So if I find an integer, if I have 2 times this integer plus 1, so if I can find a number L so that m equals this, then it's called odd. For example, if I have 7 I can write as 2 times 3 plus 1. Or 9, for example, I can write as 2 times 4 plus 1. So these are definitions of even and odd numbers. Alternatively, we can say that a number is even if it's divisible by 2. And if it's not divisible by 2, then it's odd. Okay, so all numbers that are divisible by 2 are even. All numbers that are not divisible by 2 are odd. We can also talk about common multiples. What is a common multiple to two numbers? For example, if I have the numbers 3 and 4, what common multiples do I have? What is a multiple of 3? A multiple of 3 is 3 times 1, 3. 3 times 2, 6. 3 times 3, 9, and so on. And multiples of 4 is 4 times 1, 4. 4 times 2, 8. 4 times 3, 12. And if I would continue one step more here, for example, 3 times 4, that's also 12. So we see here that multiples of 3 are 3, 6, 9, and 12, and so on. There are infinitely many. And of 4, we have 4, 8, 12, and so on. So, do they have any common multiples? Yeah, they will have infinitely many. We will come to infinitely many numbers where they have a common multiple. Here is the first one. So they have 12 in common as a multiple. But also, for example, 24, or 36, or 48, and so on. So there are infinitely many. But we can talk about the least, what is the least common multiple? The smallest number. So what is the smallest common multiple? Yeah, we see that it's 12 in this case. So least common multiple of 3 and 4, that is 12. We can also write that as shorthand LCM of 3 and 4. So least common multiple of 3 and 4 is 12. So that is the smallest common multiple of 3 and 4. We can also talk about greatest common divisor. For example, if I have the numbers 24 and 30, what divisors do they have in common? Yeah, for example, the divisors of 24 is 1, 2, 3. 3, for example, since 24 divided by 3 is 8. So we can write 24 as 3 times 8. 4, since 4 times 6 is 24. Not 5. 6 then. Yeah, 6 times 4 is 24. And then continue with what we have more. 8. 8 times 3. Not 9, not 10, not 11, but 12. And the largest one is, of course, 24. But these two are quite trivial. This is the 1 and the number itself. And 30, what do we have there? We have 1, 2, 3, not 4, 5, since 5 times 6 is 30. 6, yeah, 6 times 5 is 30. Not 7, not 8, not 9, 10, yes. 11, 12, no, 13, 14, 15, 15. And that's the, apart from 30 itself, that's the greatest one. So what is the greatest common divisor? We see that we have 2 in common, 1 in common, they have 3 in common, 6 in common, and that's the largest one they have in common. So greatest common divisor, that's 6. That's the largest integer they have in common as a divisor. So greatest common divisor of 24 and 30 is equal to 6. We can also write that as shorthand GCD of 24 and 30. So this is a number. The greatest common divisor of 2 numbers, in this case is 6. Let's look at some examples of what we have gone through so far. For example, if I want to find out if this number is a prime number. For example, if I want to find out is 21 a prime number, of course you may see directly it's not. But how would I go about for a number? Yeah, one method is that try all numbers smaller than 21. So first you try to divide by 1, of course, but that's trivial. And 2 does not divide 21, so it's not. 3 does divide. So 3 divides number. Then we have found a number that divides 21 and is larger than 1 and is not its number itself. So it means that this is not a prime number. But if I would have instead, for example, 23, Then I have to try again here. 1, but that's trivial. 2 doesn't work. 3 doesn't work. And none of the numbers up to 22 will divide 23. So none of these divide 23. Of course 23 itself. But so the only numbers that divide 23 are 1 and 23. So that means that 23 is a prime number. Okay, it's a lot of work testing all these. So one could actually limit oneself to only testing prime numbers. Because if this is not the prime number, we know it can be written as a product of prime numbers. So we actually only have to test all the prime numbers. We can skip 4. So we have to test, does 2 divide it? No. Does 3 divide it? No. 5 divide it? No. So if you have tested all prime numbers up to the number and none of them divides, then we know this is prime number. Otherwise it's not a prime number. And actually one doesn't even have to test that far. It's actually enough only to test up to the square root of the number, rounded down to an integer. But we will not show that here now. We'll leave that for the exercises. So if you have the book available, there are exercises to train on that. But in practice, it's hard work to find out if this number is a prime number or not. So you have to really test a lot of numbers. So if you have a large number, for example 2, 3, 7, 1, 9, 1. If you want to test out if it's a prime number, it's not so simple. You have to test a lot of numbers. So actually we would have to test all the prime numbers up to this. And this rounded off to the closest integer. So you have to test a lot of numbers. Another example, for example, let's say that we want to examine something about properties of numbers. For example, if you add 2 even numbers, so if you add 2 even numbers, will the sum always be even or always odd, or will it mix between even and odd? Yeah, the fact is that if you add 2 even numbers, they will always be even. But how can you prove that? So if you want to give a mathematical proof of that you add 2 even numbers, then the sum is even. To do that, you can, for example, do like this. Okay, if you have 2 numbers, you know that are both even. That means that you can write them as a multiple of 2. So 2 times some other integer, and the same for this one, some other integer. So you know this is the case. If you now add these 2, then you have 2k plus 2l. 2 times k and 2 times l. Can you show that this is even? Yes, you can, because if you factorize out, you can take out 2 in front. Because distributive, you can write it out like this. Then you see that here you have an integer. Because an integer plus an integer must be an integer. So we can call it m. So you can write it as 2 times m. So a plus b can be written as 2 times an integer. And that means that a plus b must be even. So this is a proof that a plus b must be even. So let's take another example. Let's say that we want to find greatest common divisor of 980 and 4200. And also we want to find out the least common multiple of 980 and 4200. In a later course we will see that, or later lecture, we will see that it's easier to do this for larger numbers with Euclid's algorithm. But we will here keep it simple. We will look at smaller numbers, and then we can do it by looking at prime numbers. So we make prime factorizations of our numbers. So for example, if I make a prime factorization of 980, then of course I have to test. I can test to divide by 2. I see that 2 is a factor, a prime factor. So if I divide this by 2, then I have 490, and then I can test what prime numbers divide 490, and then I can find all my prime numbers making up this prime factorization. And if I do that, I will see that the prime factorization is this one, and this is a unique prime factorization. So we have 2 2s, 1 5, and 2 7. That's the only way to write this as a product of prime numbers. If you disregard the order of these, only look how many of different types you have. You have 2 2s, 1 5, and 2 7s. And the same way you can find out that 4200 you can write as you have 3 2s, 1 3, 2 5s, and 1 7. Okay, so this will be helpful now when we try to find the greatest common divisor and least common multiple. So how can I find the greatest common divisor? The greatest common divisor is a factor. It's a number that they both have in common, and the greatest, the largest one of those. For example, they have both in common 2 and also 4, but not 8, since only 2 2s are part of the one of them. 7 is also a common divisor. But what is the greatest one? Yeah, then we have to take out all the prime numbers that are part of both. We say we can pick out 2 2s. Because you can take 2 2s from that and 2 2s from that. You can't take 3 because you only have 2 here. We can't take 3 because 3 is only part of one of them. We can take 5. Yeah, we can take 5. We can take 1 5. Since we have 1 5 in 980. We have 2 here, but that doesn't matter. And we can take out the 7, since we have the 7 in both, but not 2 7 in both. So this number, what number is that? That's 4 times 35, so 140. So 140 is a common divisor. It's a common divisor for both. So that is the greatest common divisor we have. I can't find a larger one. For example, if I want to have a larger than 140, then, for example, then if I include a 2, then I get 280. But I can't have 3 2s because there are only 2 2s of the 1. So this is a divisor of 4200, but it needs to be a divisor of both. So the greatest common divisor is to see what can we find in common here. What is the greatest thing we can find in common? And that is 2 2s, 1 5, and 1 7. And then, what about least common multiple? Okay, there are infinitely many common multiples. What is the least one? Yeah, then we want to find a number that contains both of these prime factorizations. We want to find a number that contains both numbers. So if it should contain both numbers, that is, have both numbers as a factor, then we should have all the prime numbers belonging to them. So for example, if we should have it for both, if both of them should be in common here, then we need to have 3 2s. So if the number should contain both, then it must contain 8, that is 3 2s and also 2 2s. And if it should contain both, it must contain a 3, since 3 is part of one of them. And if it should contain both, it must have 2 5s. And 2 7s it must also have. So in this case we take the larger one of all of them here. So we must have the larger one here 3 2s. You must have a 3. You must have 2 5s. You must have 2 7s. So this is the least common multiple. So these contain both. And this is the smallest one that contains both. Okay, so what do you get if you calculate that? For example, doing it by calculator, you see that it's 29,400. So this is the smallest integer that contains both. So this is the least common multiple. The last thing we will look here at in this part, number theory, is figure eight number. We will come across many more concepts later, and we look at more advanced concepts later lectures. But for now, this elementary part of the number theory, this will the last thing we look at. Figure eight number, then we need to know what is a number sequence. What is a sequence of numbers? Yeah, that's, you almost hear what it is. For example, sequence of numbers could be 1, 2, 3, 4, 5, of course, and just continue like this. Or if you look at all the even numbers, so here we have a sequence of numbers. Or the odd numbers, or the prime numbers, for example. The prime numbers constitute a sequence of numbers. And not 9, 11. So these are all examples of sequences of numbers. A particular example of figure eight numbers, because they can be represented with figures. So there are sequence of numbers, but they can be represented by figures. By the way, I should say here that it doesn't need to be infinitely many. It could be finitely many also, but normally you look at infinitely many. An example is triangular numbers. They're called triangular numbers because we can arrange them in these triangular shaped figures. So we first have 1, and then we add in the diagonal a new number of balls. So you see we start with 1, then add 2 there, 3, 4, 5. So how many balls do we have in each figure? You see it has 1, then we add 2, so we have 3. We add 3, so we have 6. Then we add 4, so we have 10. And add 5, 15. And then we can continue in the same fashion. So this sequence of numbers are called the triangular numbers. And one can show that, for example, the nth triangular number is given by the following formula. We leave that to the exercises to show that. But let us test. For example, the 5th triangular number. Does it work with this formula? So we plug in 5 here. Then we have 5 times 6 divided by 2. 30 divided by 2 is 15. And we see that matches this one. So this is a formula for giving the nth triangular number. And another example of figure eight number is square numbers. And the square numbers are called out because we can arrange them in squares like this. So we have the square of side 1, square of side 2, square of side 3. So how many balls are there? It's 1, 4, 9. So these are just the squares of numbers. So this is 4 squared, 5 squared. So of course, in this case, the nth square number is given by n squared. We can also show that, for example, the nth square number can be written as the sum of the first odd numbers, or the first n odd numbers. So for example, if I can write like this: 1 plus 3 plus 5, 7, and then I have to continue here until I come to the number 2n minus 1. For example, S4, that's square number 4. Then you have to take 1 plus 3, 5, and then I should continue until, if I plug in 4 here, 2 times 4 is 8, minus 1, 7. So I continue until 7. So if I add the first 4 odd numbers, since it's square number 4, the sum of these are equal to the square of 4, 16. So this is also a result that holds for square numbers. And it follows from this figure, for example. You see that if you have the first one, the next one you add 3 here. The next one you add 5. Then you add 7, 9. So you get the next one by adding the next odd numbers. So you get just adding 1 plus 3 plus 5 plus 7. You get the sum here will be equal to the sum of the first odd numbers. When doing number theory, this is not so much theory here really. The larger part of learning number theory is to do a lot of exercises. So I recommend now that you, at least if you have the Swedish and Norwegian book, that you try a lot of exercises, because that's really the main way of learning number theory.